All right, so I hope you're ready to dive right in. Let's go ahead and do it. So I uploaded everything on Canvas because I know that Dropbox has banned me again for, well, hosting malware, which I was for this class. So yet again, Dropbox has banned me. It's almost like becoming a yearly tradition these days. So I'll have to have another conversation with them about the fact that, yes, I am hosting malware, but it's for a good cause, for a non-malicious cause. Okay. So I posted everything on Canvas, and it should be saved there. It hasn't banned me yet. So yeah, yeah, it's called Advanced Static Analysis Techniques. Actually, yeah, it's under that label. But I think once you download it, you will see everything everywhere. All right. So let's go ahead and let's actually talk a little bit about, like, why are we doing this? Why can we not just stick to what we already know? The basic static and basic dynamic analysis. Why does it not suffice? Well, basic static analysis can definitely give us some useful information. For example, it can tell us the DLL functions which are imported by the program, for example. But remember, as I said before, we're sure whether those functions are used. All we can know is that, they're imported. Similarly, with basic dynamic analysis, we can use, for example, a tool like Wireshark in order to reveal that some packet was received. However, how does the malware actually process that packet? Like, what kind of information does it extract from it? So those questions cannot really be answered in any meaningful way using the basic techniques which we just covered. We need to probe much deeper. Okay. Now, if we go back to our alien analogy to malware analysis, so basic static and basic dynamic analysis techniques are basically sort of like, checking the texture of the skin, looking into the eyes, um, you know, uh, just studying the overall outside bodily anatomy. And advanced techniques are basically where we're actually going to cut the body open and actually see what's inside of it. So that's why we need the more advanced techniques. For example, we want to know not just whether malware imports a certain function, but does it use it? And actually, how does it use it? Because that's the $1,000,000 question. And also, for example, if we were able to establish using basic dynamic analysis that malware receives a packet, well, we want to be able to know how does it actually process it? What is the logic for that? And advanced static analysis will allow us to reveal everything that malware is capable of doing. All right. So any questions so far? Are we good? So, like I said, to be able to do malware reverse engineering, you do have to have a firm grasp of the computer architecture and assembly, basically the stuff which you learned in 240. But we will do a little bit of a review to hopefully help you either restore those skills or to build up enough of that. All right. We will be using some stuff from 351 as well. Yep. But we will get to that. Okay, yeah, because you do need to understand operating systems as well. All right, so let's get right to it. So basically, typically malware authors, they write malware in a high-level language. Typically, they would use something like C or C++. Then they would compile those high-level languages into, well, binaries. So once you compile the program, it gets translated into what's called the CPU machine code, the code which can be ran on the CPU, all right? Basically, the binary code. So just to see how that would work, so let's say that I have a C program or C++ program, which looks something like this. When you compile it, it turns into binary, which can look something like this, okay? Right here, I just use some simple example of the hexadecimal. But in reality, like all computer binaries, they are all just a bunch of zeros and ones. So basically, your high-level program gets translated into a bunch of zeros and ones, which can then be executed on your CPU. Those zeros and ones represent the executable instructions and data of the malware. Now, by process of disassembly, what we can do is we can take the binary code and we can do this assembly process, which will convert it into the assembly code. Because its sequence of zeros and ones in your binary program actually corresponds to a specific assembly instruction. So this assembler can easily decode the binary back into assembly. And then we can actually analyze the assembly code to try to understand what the program actually does. So I was asked to repeat. Okay, sure. Attackers, they write malware in a high-level language, right? And then once they're done, they compile it into a binary program. And binary program is basically a bunch of zeros and ones that represent malware instructions and data. So, and by a process called disassembly, we can take the malware binary and we can translate it back into assembly code and try to figure out what malware does, because working with assembly is much easier than working directly with binary. Okay, does that make sense?
Professor, how come we can't convert the assembly back into like a higher level language? Is that possible, or is that something that can't be done?
Yes, it is possible. It's something called decompiling, but this process is not exact. And typically, current decompilers, they are really, they produce some code that is not accurate and that is not as
Got it. It's less perfect.
Exactly. Yeah, and because you see, when I converted it back into assembly, it's very accurate and precise, because like each sequence of zeros and ones in your binary actually encodes a very specific assembly instruction, if you know what I mean. So
thank you.
There's a one-to-one mapping. Mm-hmm. In fact, you can easily write your own disassembler. All you have to do is just read a sequence of zeros and ones. Like in case of x86, read 32 bits at a time, and then just decode it into the appropriate instruction. So, yeah, attackers would occasionally use some binary code directly. Sorry, not binary. They would use some assembly to write malware directly. But most malware is written in a higher level language. So, and Ali's asking, why can we understand malware's action from high-level languages? Well, you could, but malware authors very rarely give you the code to go with their malware. Typically, all you would be able to get in the real world is a binary, right? Attackers don't publish the code for their malware. Oh, by the way, here is the code for my malware, so it'll be easy for you to analyze. Just doesn't happen that way. All you're going to get is a binary in the real world. So, I mean, of course, you can understand the function from the higher level language, but the point is, you won't usually get the source of the malware. Does that make sense? So, yeah. So basically, that's the idea. So that malware analysts can get non-competitive and they high-paying. Yeah. All right. Do you have any other questions? All right. Great. Now, it turns out, folks, that now, if this is your level of understanding of how programs are compiled and then later disassembled, in most cases, that should be fine for malware analysis to work at those levels of abstraction. So, like, you have your high level implementation, you have the compiled executable, and you can take the compiled executable and you can disassemble it back into the assembly language. But just to be perfectly accurate, there are actually 6 levels of abstraction when it comes to program compilation, translation, etc. So what I would like to do is I'd like to go over those, because in some cases that could become important. Okay, so I'm going to start at the lowest possible level, which is the hardware, And then we're going to work our way up to the highest level, which is the high-level language. So basically, your hardware is a bunch of ANDs, ORs, and XOR gates, and they are connected in such ways that cannot be easily manipulated by the software. So it's very inflexible, it's very hard-coded. So that's basically your hardware. The logic is implemented like literally in a hard-coded way, okay? It's your computer architecture. It's built in a certain way, and it can do only certain things. It cannot be easily manipulated by the software. Now, then you have something called the microcode, which sometimes you may hear being referred to as the firmware. So microcode is a set of very simple instructions that were specifically designed to execute on your computer architecture hardware. Okay, sometimes you'll hear to them being referred to as the micro-ops as well. So, like once again, it's the very low-level instructions which are designed to execute on a specific kind of hardware. Typically, in your everyday malware analysis, you generally don't get to work with a microcode. You get to work with one level higher, which is the machine code that we'll talk about in a second. But that's microcode, okay? It's designed to execute on a specific hardware. And then you have the machine code. So machine code is basically the binary program. Okay, that's the file into which your programs are compiled into, and the machine code can be disassembled into low-level language like assembly. Okay, so if I open up my binary program, what I'm going to see is the machine code, and machine code can be disassembled into assembly. And then finally, we have the high-level language. And your high-level language is basically your C, C++, any kind of a compiled language. So basically what happens is that so you're going to write your program in a high-level language such as C or C++. When you compile it, it will be compiled into the machine code, which could be disassembled back into the low-level code like assembly, which is easier to understand than the machine code. And then you have, and then when you actually try to run the machine code on the CPU, it will be translated by the CPU into microcode, which will be the actual instructions that are executed. Okay? So that's basically the idea. Now, this only talks about the compiled programs, but there are also translated programs or interpreted language. So interpreted language adds another level of abstraction to this whole thing. So the way in which it works is as follows. So if you have a language like Java, for example, so Java isn't a compiled language, it's an interpreted language. So the way in which it works is you write your Java program, and then the Java translator compiles it into intermediary form called bytecode. So bytecode is designed to run on what's called an interpreter. So now, Java is a cross-platform code, so there are interpreter programs that are developed for different platforms. For example, there is one for Windows, there is one for Linux, and there is one for Mac, etc. And you can take this bytecode and you can execute it on any interpreter. So basically, what the interpreter will do is it will translate your bytecode instructions into the machine code instructions. And then basically the same thing happens as with a compiled language. So basically the machine code will be translated by the computer hardware into microcode, which will then actually be executed. Okay? So those are your 6 levels of abstraction. All right? as Carl was asking. So 6 levels: 1, 2, 3, 4, 5, and 6. Okay. And Joseph is asking, the interpreter does equivalent action as a compiler, but for interpreted languages. Well, yes, you can say that, yeah. Except, the difference is that, but there is an important difference though. The compiler, it translates a high-level language into the machine code. So basically, you go from higher level language into machine code, whereas interpreter doesn't interpret high level language into machine code, but rather it interprets the bytecode into machine code, because bytecode is an intermediary form, right? Because bytecode, for example, if we're talking about Java, right? When you take a Java program and you compile it, it takes the .java file, which is your Java source file, and it creates it creates another file called .class file. It's like if my program was called hello.java and I compile it, quote unquote, in Java, it creates a file called hello.class, and then the .class file contains the bytecode, which can then be executed on the interpreter. But bytecode is not the high-level Java language, if you know what I mean. So the biggest difference is that, once again, compiler translates high-level language into machine code, whereas interpreter translates the bytecode into the machine language. So interpreter doesn't translate high level language into machine code, but rather bytecode. So like there is an intermediary form, if you know what I mean. Does that make sense? And and that's why they say Java is a cross-platform code, because I can take my Java code and once I translate it into the bytecode, I can run it on any platform for which there is Java interpreter. And like I said, there is a Java interpreter for Linux, for Windows, almost any system you can imagine. And that interpreter will be able to consume that bytecode and translate it into the machine code for that platform. However, when I compile, for example, a C++ program, let's say that I compile it in Linux, let's say that I compile it on a 64-bit Linux, and I create a 64-bit Intel Linux executable, right? I will not be able to run that same code on another computer architecture or another platform, because the machine code for those can be different, if that makes sense. Does that make sense, Joseph and Carla? Yeah. Yeah. That's why Java developers, they're always very, very, very proud, saying that, Java is cross-platform. You can run it anywhere, which is true. So, yeah. But yeah. But let me ask you, like sort of a follow-up question. You folks kind of covered, compiled language versus interpreted language back in your introduction to programming courses, haven't you? Right? They probably mentioned the concept, right? Yeah. And did they? They never mentioned that. Oh, okay. Well, yeah, that makes me very, very sad. Yeah. So basically, and so sad that I have to, to grab my Maneki Neko and basically rub his head. Hopefully that he will send us some lucks. So yeah. So well, I'm here to hopefully correct that evil, okay, that you've been dealt with. I'm sorry about that, folks. I apologize on behalf of our program, or whichever program you've been through. But basically, one question which I'd like to ask you that is related to this, right? So probably when your professors talked about compiled language versus interpreted language, they might have told you that compiled language tends to be faster than an interpreted language. And they're right if they said that. But based on this diagram, can you explain why that is? Like, why would a compiled language be faster than an interpreted language? Yeah, as Carla points out, because the interpreted language has extra steps. But I think another person wanted to say something, so please go ahead and say it, because I want to hear everyone's take. Yeah, it's closer to the machine language, right? Because when it comes to the interpreted language, right, like you have to go from bytecode to machine code, and then you go through all of the other steps. Whereas when I have a compiled language, I go directly from machine code through all the other steps. So basically, that's the idea. So, and yes, interpreted language has to be reinterpreted on every run. Yeah. Yeah, basically, this bytecode would have to be reinterpreted every time when I run it. Yeah, for sure. And Zach is asking, how does a GRE resolve between x86 and x84? Well, basically, it's all up to the interpreter. So to be able to run Java on any system, first you have to install the Java virtual machine. And when you install the Java virtual machine for a particular platform, basically it takes care of all of the architectural issues for you. So yeah. Yeah, there is a bit of a history behind why Java is kind of like that. Back a while ago, Sun Microsystems, who were the original inventors of Java, they were going to build a killer system that was going to be like the best system ever built, and Java was going to be the language that runs natively on that. But somehow the project has never materialized, and so Sun Microsystems was left with a question of, okay, so is there anything we can salvage from this project? And one of the things was, well, maybe this Java language might be promising, but the Java language was designed to run on the platform that was never developed. So basically, they have created a virtual platform, and that's why Java runs inside a virtual machine to this day. So yeah, it's a happy accident. By the way, I learned a new word from one of my health conscious friends. Have you ever heard the term snackcident? Like snack accident? Like apparently that's when you have accidentally, indulge on a snack that was really tasty but not quite healthy and with a lot of guilt. So, oh, there we go. Yeah, some of you are having that right now. And while we're on the subject of snacks, I do teach web security, and not by accident, right? We do everything with intent, right? And we're not ashamed. Yeah. Have you ever heard the term in web design called snackable content? Yeah, basically snackable content, that's an actual term, you can look it up, but it's a term in web design. It refers to the content on the web page which the user can glean by like very casual inspection and a quick visual stare. So, like for example, the snackable content for the CSF website would probably be, the big news story, right? Something which you can very easily glean, the information which you can very easily glean with minimal effort. So, that's they refer to that as snackable content. So, yeah, just something I thought I'd bring up for your other classes. And web developers, they suggest that when you're developing a website, snackable content is very important. All right. So, any questions about the 6 levels of abstractions? Please don't mix it up with 10 levels of hell. If you read, Dante's Inferno, he talks about levels of hell. Okay. So that's basically the idea. All right. So now, one of the things which I like to remind you of, I kind of touched upon this briefly in the last class, but how the machine code looks like depends on the platform. So basically, there are many computer architectures out there, and each one has its own assembly code. For example, the one we're looking at is x86. But there is also x64, which is basically the 64-bit version. There's also Spark, PowerPC, MIPS, ARM, and so much more. So, and they all have different assembly languages. All right. So ARM, well, ARM is very popular on mobile, but it's not used just on mobile. For example, Raspberry Pi is using ARM. A lot of IoT systems use that. Yeah, it uses ARM, and there are actually some ARM-based stationary systems. A lot of stationary systems use ARM. Yeah. New MacBooks, I think, too. Yeah, that's actually a good point, Joseph. Yeah. So, yeah. And the reason why different systems have different assembly language is because they have different computer architectures. Because you see, the hardware is designed to recognize certain instructions. When you took to 40, they probably talked about it, but the hardware is designed to consume a certain instruction set. So, and different computer architectures have different instruction sets because they were designed for them. So, yeah. Is ARM true real time? It can be. It can be. There are versions of ARM that can do real time. Yeah. Yeah, but real-time processing depends not only on the computer architecture, but it also depends on the operating system and the program. So, yeah, I've done a fair amount of real-time programming as part of my internships and other parts of my career. All right. So, and there are many kinds of assembly out there. So, and like we talked about in the last class, there is a very nice website which illustrates that point. And the website is called www.gotbolt.org. And as we're learning this, I highly recommend that you make this website your BFF, because you will definitely find it like what's a good word? You'll definitely find it ridiculously useful. Okay? So, and yes, you can use it on the exam. So basically just, read their agreement and then agree to it. So basically what it allows you to do is it allows you to take a C code, which you type on the left-hand panel, and then on the right-hand panel, it will convert it into assembly. Now, you can choose the target platform. So for example, right now, it's the assembly code that is generated by the GCC compiler for an x86-64-bit platform. Yes, folks, the assembly code that is that your program ends up being also depends on your compiler, because that's the compiler's job. The compiler is going to take your high-level language and it'll convert it into the machine code. And then, of course, the machine code can be directly mapped to the assembly code. But different compilers have different techniques for generating the machine code. It depends on a lot of things. One is simply the algorithm which the compiler uses to generate the machine code, because there are different machine code equivalents to generate the same high-level code, and different compilers use different algorithms. It also depends on the platform. So, for example, different platforms work in different ways. So compilers try to optimize the code for the specific target platform. So that can also affect the code that is generated. So that's why you get to choose not only the computer architecture, which in this case is x86-64, but also the compiler. So this is GCC, the Linux compiler, but if I choose Visual Studio, for example, which you can do, it'll probably look a little bit differently. Let's write a very simple program. I'm just going to do something ridiculously simple. So I'm going to do like int main, for example. And I'm going to do, for example, something simple like int a equals 1, like int b equals 2, and then int c equals a plus b. Okay, something very, very simple. So, and as you can see, it has generated the assembly code. Also, folks, please note another thing, that on how Godbolt is being really nice to me. Do you see how it maps everything for me? So, like for example, the this red line right here, okay, it's being mapped to this red line right here. So basically, it is telling me that that one line of C corresponds to those what 1, 2, 3, 4 lines of assembly. Make sense? So it's really useful. Now, what happens if I now choose a different architecture and different compiler? For example, let me choose x86 and Microsoft Visual Studio. Let's see, where is it? x64 Microsoft Visual Studio. I'm going to do x86. There we go. So, and as you can see, there are different versions of x86. So I want to do x86 with Microsoft Visual Studio, and I'll choose version 19.27. Okay. You can choose others, or I can choose this one. Yeah, let's do this one, the latest. And as you'll see, the code will probably change a bit. Boom, see? Do you see what's going on, folks, right? Now, let's say that I now choose a completely different platform. Let's say instead of x86, I choose ARM. You know, let's see, can I do ARM 32? Does it have that option? ARM 64. Okay, fine. I'll use ARM 64 6.4. Just watch it how different the assembly will look. You see, the instructions are completely different. Everything is completely different. Does that make sense, folks? So as you're learning to master this, you will, Godbolt is definitely going to be your friend. Okay? Yeah. Is there a way? And Carl is asking, is there a way to get a literal translation? This is a literal translation. This is a literal translation. It basically takes every single machine code, every single piece of machine code that would be generated by this compiler and translates it into its assembly instruction. So yeah, this is a literal translation. There is this is not a game. Like yeah, this is for real. This is a literal translation. All right. So any questions, folks, so far? Questions? Can we translate from assembly to higher? No, Godbolt does not allow decompiling. Okay. Yeah. All right. All right. Great. So let's continue on then. Yeah. Oh, and before we continue, folks, I just wanted to ask you a quick question. As you know, the next assignment is up. It has to do with basic dynamic analysis. And to help you better understand things, I actually included a tutorial, actually 2 tutorials, which do an in-depth analysis of the few practice samples. I hope you found those useful. And if you have any questions, please feel free to let me know. All right? Now, folks, before we go on, I also would like to talk about something extremely important in computer architecture in general, which is one of the most fundamental things, and it's the concept of the Von-Neumann architecture. What is Von-Neumann architecture? Well, basically, it is the architecture of most modern computer systems. It's called the Von-Neumann architecture because it was designed by a scientist named Von-Neumann. He's one of the gods of digital revolution. And he actually contributed to so many fields, and the Von-Neumann architecture is actually one of his minor contributions. But it is a revolutionary thing in computer science. So, yeah, I mean, he was a genius, and there is no easy way to say that. One of my students who actually researched Von-Neumann passionately, they actually said that he was, he was even a great drinker apparently, because he could drink anybody under the table in any drinking game. I haven't verified that, but they said that they researched that. So, yeah, when your minor contribution is revolutionary, yeah, he was just that awesome. Yeah, so as you are using your computer, Von-Neumann is one of the people you have to thank. And you folks probably learned about Von-Neumann architecture in your 240 class, right? Or your introduction to computing. You did, right? Great. Yeah, so, or 440, yeah. Yeah, so I would like to quickly, review what it is, because it will help us understand a little bit about malware and, hacking as well, because a lot of it actually ties back to the Von-Neumann architecture. So what exactly is Von-Neumann architecture? So basically, a Von-Neumann architecture consists of the following components. So you have the ALU, which stands for the arithmetic logic unit. It is a hardware component that actually does the computations. For example, it does all the additions, subtractions, and performs most of the computations associated with common programs. Now, in order to be able to do a lot of operation, the CPU needs little memory buffers called registers. So registers are typically small hardware storage units, um, which are used to store the data on which the ALU is operating. So, for example, when the ALU needs to compute a sum of two numbers, one operand number will be stored in one register. Then the second one would be stored in another register, and then ALU can be told to add up the contents of those registers and then store the result in some other register. Okay, so registers are typically small storages, small storage units, which can be used in order to store the data on which the ALU is operating. Now, of course, registers are typically not enough to store entire programs or big quantities of data. And that's why you have your RAM, or your random access memory. That's what RAM stands for. So RAM is the random access memory, and the reason why it's called that is because I can basically access arbitrary memory location in any order with roughly the same latency. Okay. Typically, RAMs are volatile, which basically means once you cut off the power, all of the data in it is gone. But just a quick disclaimer, since we are in a security class here, there was a study done back in 2008, which I have reviewed quite thoroughly because I worked on a similar research project related to virtual machine checkpointing security. And it turns out that actually our RAM might not actually be as volatile as we thought it was. Like, for example, when they did this experiment, they would basically store some data in RAM, and then they would power down the system and then try to dump the data in RAM after certain periods of time have elapsed. And they were able to recover data like even half an hour after the system power was turned off. Okay, so, and the implications of this is, like, let's say that you power down your computer, you think your data is safe. Well, somebody can take out the memory chips and they can basically dump the data on them for quite a while. Apparently, you can also increase the data persistence in RAM if you take the memory chips, those RAM chips, and you dunk them into the liquid nitrogen. The liquid nitrogen is the super cold liquid. Its boiling point is basically room temperature. So whatever you put into it basically just freezes right away. Don't put your hand in there. I played a lot with liquid nitrogen when I took the physics class, and our teaching assistant, who was basically almost our age, and on the last day of our lab, he basically entertained us by taking a huge bucket of liquid nitrogen and dumping it all over the lab. And it was quite a show because basically, it boils at room temperature. So you get bubbles, running across the room, crazy as they're evaporating. So yeah. So the point is, if you put the memory chips into liquid nitrogen, you can preserve the data there. So yeah. So this is something, just like as an FYI, that because everything your computer operates on, if it's stored in RAM, it is stored in RAM. And in my research project, where we, if you're interested, I can give you the papers that we published. But we were studying the security of virtual machine checkpoints. Yes, basically what happens when you take your VM and you take a snapshot of its memory. Well, what happens if your VM had, was processing passwords? Well, guess what? The data can be in your RAM, and when you save it to a checkpoint, the data in RAM, which was not as persistent as you thought it was to begin with, it is now saved into persistent storage. So basically, the data now persists. So if the attacker compromises the checkpoint file, they will be able to extract the data in the checkpoint. So like for example, what happens if you typed sudo in Linux and you typed in your password and then you checkpoint the VM? In our study, we were able to find clear text password that is stored in multiple parts of memory. Like, for example, it is stored in the pseudo memory, it is stored in the operating system buffers at multiple levels, and all of that. Clear text, yes, clear text. So, and we developed something called a secure checkpointing mechanism, which basically allows the user to say that when you checkpoint this VM, I don't want you to save any memory from the Firefox process, because I have previously typed some sensitive stuff into there. So basically, it would save everything to the checkpoint, but not the Firefox process. So the memory, the Firefox process, would be not saved. So anyway, if you're interested in that, I can definitely share some of the papers that we published on that subject. So yeah. So anyway, just a bit of a what we think to think about, and perhaps the other thing to think about is that nowadays they have another memory technology called NVRAM, which stands for non-volatile RAM, which basically means that the data stays there when you cut off the power, which is great. For example, if you were working on your computer and the power went out, so you won't lose your work, but it does increase data persistence almost indefinitely. So yeah. And the question about password managers, password managers, they rely on your operating system. So if the operating system stores your data in some plain text buffer, that can end up in checkpoint in a clear text. So yeah, that's basically the idea. So anyway, that's a bit of a primer on your RAM, what it is and how it works. And basically, ALU can also make use of RAM, which is a bigger form of storage, but a much slower form of storage than the registers, because the general rule of memory technology is the bigger it gets, the slower it becomes. So, and in order for ALU to be able to fetch data from memory and to save data from memory, it uses something called the control unit. So the control unit is basically responsible for fetching the data from RAM and writing the data to the RAM. Okay? So another part of Von-Neumann architecture is the I/O devices. So let's say that your LU needs to get some data from an I/O device, for example, a keyboard, a network device, etc. Well, it can also do that. And typically, there would be some kind of an I/O control unit in between, though it's not always specified explicitly in all such models. So, what is the one most distinguishing feature of the Von-Neumann architecture? What makes it so different from other architectures, such as the Harvard architecture? Well, folks, and this is important, this is the most distinguishing part. The most distinguishing part of the Von-Neumann architecture, executable instructions and data are all stored in the same physical memory. If you compare it to, for example, to the Harvard architecture. In the Harvard architecture, you have two different RAMs. Like there is the instruction RAM, which only stores the instructions. I'll call it IRAM, and there is another RAM which only stores the data. Okay, I'll call it DRAM. Nothing to do with the DRAM technology, just my abbreviation. Okay, but when it comes to the Von-Neumann architecture, it basically merges them together. So both executable instructions and data are all stored in the same physical RAM. Okay, now, so what are the security implications of storing both data and instructions in the same RAM? Well, your basically, your program doesn't really have a way of distinguishing between data and executable instructions. So there are some security attacks that are based around making your program confuse the data and the executable instructions. For example, let's say that you have a program that has a buffer overflow vulnerability. Basically, what the attackers end up doing is they end up stuffing your buffer with so much junk data that they pass the buffer bounds, and they basically override the part of the neighboring memory that contains executable instructions. And they override that part of memory with their own instructions. So when your program executes, it essentially ends up executing the instructions that were injected by the attacker. Okay, so basically, because the data RAM and instruction RAM are essentially the same physical device, it is very easy for the program to confuse between instructions and data, which gives an opportunity for attackers to inject some bad data into your program and thus make your program confuse the data and executable instructions and basically trick it into executing instructions. Okay, does that make sense, folks? Are we good? All right. So like once again, folks, the distinguishing feature of the Von-Neumann architecture is that instructions and data are all stored in the same RAM. If somebody asks you that on the interview, that's basically what you're saying. Okay, that's the idea behind this one. And once again, I did summarize all of that here in case you happen to forget. All right. Yes, Harvard architecture is still used in some architectures. For example, some embedded architectures they have different instructions for data and RAM. Yeah, yeah. So Harvard architecture is not dead, but a lot of home computing systems, for example, in servers and other kinds of systems, they use Harvard. Okay. Now, folks, also, in order to be able to do malware reverse engineering, we also have to review how is the memory of a typical process structured. Keep in mind, when you execute your program, when you run it, it becomes what's called a process. A process is basically a program in execution. Hopefully you learned that in your OS class. And basically, your process memory consists of the following components. This is a high-level summary. The order of those components may vary, but the idea is the same. So typically, the first component is called the code section. Sometimes you'll hear it being referred to as the text section, the executable section, etc. But basically, this is the part of your process memory that stores the executable code. So that stores the instructions that the process is executing. So that's basically the idea on what a code section is. Now, the next section is called the data section. So data section will typically store two things. Number one, it stores the global variables in your program. And hopefully you all know what global variables are. They're the variables that are accessible throughout the entire program. And there is also the static values. So static values are the values that cannot change during program execution. So for example, if you declare a constant in your program, well, it'll be stored in the data section because constants, by definition, cannot change. All right? So any questions so far, by the way? So then we have the next component, and it's called the heap. So the heap stores what's called the dynamic memory. The dynamic memory is basically the memory that is allocated during the process runtime. Unlike the other kinds of memory that is allocated either during compile or load time, the memory stored on the heap is allocated when your process actually runs. In your programming lives, you probably saw dynamic memory being allocated using functions such as malloc in C, or in C++, there is the new function or the new keyword. So when you did something like this, for example, new char 100, for example, basically what you did was you told or you asked the operating system to allocate 100 characters on the heap. Each character is typically a single byte, so somewhere on the heap it would allocate enough space to store 100 characters, which would typically be 100 bytes, and it would return a pointer to that memory. So typically, you did something like this. You get char star pointer, and I'll call it p equals to this. So basically, new would allocate 100 bytes on the heap, and then it would return a pointer to the beginning of this memory, which would then be stored in P. So basically now you have pointer P that is pointing to the 100 bytes that are stored on the heap. And of course, you probably learned that whatever is allocated on the heap, it is not deallocated until you yourself deallocate it. So for example, if this was C++, I would have to do delete brackets, P, right? Which would basically deallocate those 100 bytes on the heap and make that memory available for other things. Okay. Otherwise, I get what's called a memory leak. Okay. Memory leak is when I lose all the pointers to the memory on the heap. And the heap memory will not be deallocated until I either deallocate it myself by calling delete in C++, or until my process terminates. Because once the process terminates, its entire memory will be deallocated, and heap is just part of that memory. All right. But if you keep allocating new memory, but you don't deallocate it, your process may eventually run out of the heap space. So, and eventually you'll get to the point where you will call new, but it won't be able to allocate more memory because you'll be out of the heap memory space. And the way in which that manifests is that new will typically return null. Okay, if new returns a null pointer, that basically means that's new's way of saying that I couldn't allocate the memory which you asked me to allocate because you're out of heap memory. Should have listened to your 121 instructors, right? So that's basically the idea. And a quick review here. I have a question for you. What happens after I do delete P and this memory is deallocated? What is P called now? What is the name for that? So I'll give you a hint. Yeah, dangling pointer. Very good, right? Because why? Because P is still pointing to the beginning of this memory, but this memory has been deallocated. Okay? So in other words, P is no longer pointing to a valid memory address which was allocated. So that's why your professors probably told you that as soon as you delete, as soon as you deallocate the memory by calling delete, you should probably do something like this by saying p equals null. Okay, not required, but definitely great programming practice. Okay. So any questions so far about the heap? All right, great, excellent. Now, another important component, which we will spend a lot of time talking about because it turns out it'll play some very important roles in malware analysis, is the stack. So basically, stack actually grows from higher memory addresses to low memory addresses, unlike the heap, which grows from low memory addresses to higher memory addresses. So we can pretend in this case that this is address 0, the first memory address that is accessible by the process, and then my memory addresses increase this way. Now, as I allocate more and more stuff on the heap, typically, my heap is going to grow from the lower memory addresses to higher memory addresses. Stack is the opposite. Stack starts at a high memory address, and as you add more things onto the program stack, it will basically grow from higher memory addresses to lower memory addresses on a collision course with the heap. All right? Now, what does the stack actually store and what is it used for? Well, the stack stores, in a very brief summary, a function called history. Because, folks, as program calls one function, that then calls another function, that then calls another function, we need to be able to keep track of all of those function calls. For example, I need to keep track of the function variable values. I need to be able to keep track of function parameters. I need to be able to know where should the execution of the program proceed once the function has finished. And all of that is stored on the stack. So basically, the stack stores local variables of each function in progress, all parameters of the function, and the return address, which is the address of the instruction where execution should resume once the function has returned. Okay, so any questions so far? All right, so let's study stack in a bit more detail, or let's actually study it a little bit later. First, I want to review a few instructions in assembly. All right, folks. So like I said, this is going to be a crash course in 240. So let's study a little bit about x86 instruction set and how it is formatted. So basically, every single x86 instruction, it'll have the following format. It consists of something called a mnemonic, operands, and that's basically the idea. I said 3, it's actually 2. So basically, a mnemonic is a word that is used to briefly summarize what the instruction does. So for example, the MOV instruction mnemonic stands for move, because this instruction is responsible for moving the data, for example, between registers or between registers and memory. And then we have operands. The operands can be registers, they can be memory locations, or they can be data. So for example, this operand right here, it represents a name of the register. As we'll learn a little later on, that the x86 architecture has multiple registers, and one of those registers is named ECX. And then I have something called the source operand, which basically is a literal value. Like, it's a hexadecimal value 42. So overall, this instruction basically says that I want to move the value of 42, the hexadecimal value of 42, into the ECS register. Okay, so that's the mnemonic. I'll just use M for that. And those are the operands. I'll call them ops. Okay, now different instructions, they can have a different number of operands. Some instructions will have 2 operands, like this one. Some will have 1 operand, and some will have 0 operands. Some may have, I think, like even 3 operands. So that's actually one of the ugly things behind the x86 instruction set. But you will see what I mean later in that regard, right? So any questions? I hope, folks, this is just a review from 240, right? You've seen all of this in 240, correct? Great. So, but I hope this review is not a complete waste of time. I hope that it'll help you refresh, because I do realize that you probably took that quite a while ago. All right. So, yeah, I figured we may need refreshers. Now, so I'm not going to go into this part in detail, but basically every single assembly instruction has a one-to-one correspondence with a specific machine code. So here's an example. Here is the instruction from the last slide, which basically tells us to move a literal value of OX42 into the ECX register. This is how it would be translated into the machine code. So basically, and the way in which the x86 machine code works is as follows. First, you have something called the opcode. So the opcode basically tells the CPU which instruction you want to perform, and then you would have a bunch of instructions which tell you about the operands. So, like, for example, this instruction, move ECX OX42, it would be encoded as B9 42000000. Okay? So, and Carl's asking, is there a way to translate machine code into assembly code for us? Yep. And we will be doing that very frequently when we analyze malware. Because once again, when you analyze malware, I mean, you basically get, the machine code, right? You will get basically, this. And we're going to be using this assembler tool, which will convert this into assembly code, okay? Now, also, another important thing to remember is that x86 encodes all of the instructions and data using something called a lib format, and what is its counterpart called the big endian, okay? Can you folks hear me? Is everything okay?
You cut out for maybe 10 seconds there, but I don't know. I think you said little endian, right?
Yeah.
Okay.
Yeah, basically, all I said was that one of the things to be aware of is that x86 architecture, it encodes everything using a little endian format. So, and I just wanted to review what the little endian and its counterpart, the big endian, are. So if you heard that, you basically, you heard it all. Okay? Make sense? So now, one of the things which sometimes I hear people say is that big endian is backwards. Some people say the little endian is backwards. Well, in reality, none of them are really backwards. It's all relative. And hopefully, you will remember that after this review. So first of all, what exactly is endianness? So basically, endianness refers to how the system interprets multi-byte values. Okay, it doesn't apply to single byte values. It only applies to multi-byte values. And folks, a quick review on multi-byte values. When we deal with the multi-byte values, please recall that when I encode a byte using hexadecimal format, each hexadecimal digit is 4 bits. So like if I use something like OX3, well, basically that's 4 bits. Okay. So if I do something like this, let's say 3A, now this is 8 bits long. So basically a single byte is always 2 hexadecimal digits in length. Okay, that's just how it is. Where 3 represents the 4 higher bits of the byte, and A represents the 4 lower bits of the byte. But a single byte is always 2 hexadecimal digits. So endianness doesn't apply to single bytes. It only applies to multi-byte values. So like, for example, let's say that I have a number such as, for example, 3A, and I'm just making this up, 4D. My question is, how many bytes is this value? It's 16 bytes, right? And, well, is it 16 bytes? I think you might say 16 bits, right? So this one, right? It's 16 bits or 2 bytes, right? Right? Because each byte is 8 bits, right? So it's 2 bytes. Because remember, like, once again, each byte is 2 hexadecimal digits long, right? So, and if I have something that is 4 hexadecimal digits long, it means it's 2 bytes, right? With each hexadecimal digits occupying 4 bits. So 4 bits, another 4 bits, another 4 bits, and another 4 bits. Okay, yeah. And sometimes you will hear the 4-bit quantity being referred to as a nibble. Okay, N-I-B-B-L-E, nibble. Okay, so like 3 is 1 nibble, A is another nibble, etc. Yeah, that's true. And also nibbles is, it used to be another way that people would refer to the snake game. You know what a snake game is, right? It's basically, the and is getting bigger and bigger while trying not to collide with anything. If you haven't played it, well, you should, just for the cultural education. Okay? That's your homework, to play Snake if you haven't. All right? So basically, endianness refers to how do I store multi-byte values such as this one. Well, there are 2 ways. One is called the big endian, and the other one is called the little endian. Now, the term where those terms come from is kind of interesting. They come from literature. There is a very famous book called Gulliver's Travels, which talk about the traveling of a man named Gulliver to the different fantastic countries. And basically, in this one country that he travels to, there are 2 warring tribes. And basically, those 2 warring tribes, they sort of have like a religious kind of warfare. And the warfare is over what is the right way to eat an egg. You know how the egg has like the little end, and then it has like the big flat end? Well, the little endian tribe would start eating the egg from its small end, and the big endian tribe would eat the egg from the big end, the big endian. So they had the little endian tribe and the big endian tribe, and of course that difference was enough to have a warfare and to kill each other over that principle. I mean, good thing that Gulliver's Journey is a fictional piece of work, and people don't kill each other for the dumbest reasons in the real life, right? Yeah. All right. And by the way, Gulliver's Travels is a great book to read, and you should probably read it for your cultural education as well. So that's where the name comes from. It comes from the names of those tribes. But what are the big endian and the little endian? Well, basically, big endian says that the way to store multi-byte values in memory is that you start with the smallest possible address. Now, folks, a quick review. The most significant byte of a value, so let's say I have a multi-byte value right here, its most significant byte is this, right? It is the first byte from here. This is the second most significant byte. This is the third most significant byte. And finally, this is the least significant byte. Okay? So now, the big endian says that the way in which you store multi-byte values in memory is that you take the most significant byte and you store it in the smallest address in memory. So for example, let's say that I decided to store this multi-byte value in memory where the first byte address is 1000. So I would take the most significant byte, which is 90, and I would store it in the lowest address. Then I would take the next most significant byte, and I would store it in the next lowest address, which would be the address 1001. Then I would take the next most significant byte, and I would store it in the next smallest memory address. And finally, the least significant byte will be stored in the highest memory address. Does that make sense, folks? Does the big endian make sense? Yeah, awesome. Now, as you know, the big endian has a little brother called the little endian. And the little endian sort of takes the opposite take on this whole thing. The little endian says that the least significant byte should be stored in the smallest address. So basically, the least significant byte of this multi-byte value is CD. So basically, it says that we have to take the least significant byte and we have to store it in the smallest memory address, which in this case will be 1000. Then I take the next least significant byte and I store it in the next smallest address, and then the next least significant byte stored in the next smallest address, and finally the most significant byte is stored in the highest memory address. All right, does that make sense, folks? Now, here is one interesting misconception about big versus little endian. Some people say that one of them is backwards. Which one of those is backwards? Okay, Carla says both. Okay, and she's kind of on the right track on this one, because and Aiden says it's big endian. And folks, the right answer is it's actually all relative. None of them are actually quote unquote backwards. Okay, because it depends how I write out the addresses. If you notice here, I wrote my addresses from to increase from right to left, right? So in this case, it appears as if the big endian is backwards. Now, what if I did now something like this? Let's say that now I decided to, that I decided to write my addresses in a different way. Let's say that I decided to write them as, it also switched my slides, that I decide to write addresses now like this, to increase from right to left. So here I have 1000, then I have 1001, I have 1002, and 1003. Okay, and then let's do the big endian and the little endian again. So I'm going to do big and I'm going to do little. And yes, because I'm so clever, I used the caps. See what I did there? No? Okay, I'm just really pleased with myself, and I want you to know that. Small things to be proud of. All right? So now, let's do, okay. I said, let's do big and little endian again. Okay? Exactly the same problem. So basically, right now, we're being told that the big endian tells us the most significant byte is stored in the smallest address. Well, okay, so the most significant byte of this number right here is 90. So we store it in the smallest address, and then the next most significant byte is AB. So we store it in the next smallest address. So that'll be AB, followed by 12, followed by CD. And then let's do the little endian. The little endian tells me that the least significant byte is stored in the smallest address. Well, okay, I start with a least significant byte, which is CD, and I store that in the smallest address, which is 1000, and then I do the next, 12, AB, and finally 90. Now, let me put this up against the previous one. So which one is backwards now? You see what I mean, right? So here, when I write my memory addresses from right to left, it seems like the big endian is backwards. And then right here, when I write my addresses from left to right, now it seems as if the little endian is backwards. All right? So none of them are really backwards, if you know what I mean. So why do you care about endianness? Well, there is actually a good reason for that. And the reason for that is when you do malware analysis and you disassemble things into machine code, as Carla points out, then everything in the machine code, all the data, is going to be stored in the little endian format because x86 is based on little endian. So for example, let's say that you have an IP address 127.0.0.1, which is basically the IP address for your local host. And typically the way in which IP addresses would be stored is that each value would be converted into a byte, also sometimes referred to as the octet. And so 127 in hexadecimal is going to be, I do have it in the slides, but I just wanted to show you. It's going to be 7F. So basically, your IP address will be just a bunch of bytes in memory, where the first byte is going to be 7F in case of 127.0.0.1, then 0, 0, and 1. So now, if you are dealing with a big endian format, then it'll probably look something like this, okay? Provided that you're reading addresses from smallest on the left to largest on the right, okay? It'll be stored like this if you're dealing with a big endian system, but if you're dealing with a little endian system, it'll look like that. So hopefully, you will be able to, to look at this and spot immediately saying, oh, that looks like a 127.0.0.1 in little endian. Now, the tools which we'll be using, such as IDAPro, they can actually help you by, by translating everything into a format where addresses increase from left to right and basically write it so it is written in the way in which you're used to it. But keep that in mind, okay? Everything, all binaries which we'll be looking at, their memory is going to be in little endian. Okay? Oh, and Carl is asking, are we going to be using the snake in this class? Yes. So, yeah, snake is the name I use for Python. So, yeah, once in a while, we'll probably be using Python to do things like conversions from base 10 to base 16, like I just used. In Python, I can easily convert a base 10 number, like 127, into a base 16 number by doing hex, and it'll give me the hexadecimal equivalent. I can also convert things into binary by doing bin and 127, which will give me, the binary value of that. So just a quick, heads up on Python. All right, folks. So I think it's our break time. So I will let you go ahead and take a break. And then after this, once we come back, we will review some more assembly instructions and then jump into the assembly stack. Now, folks, I am aware that assembly stack is something that people have been known to have some thoughts of, banging their head off the table, throwing stuff out the window, performing less than gracious acts on others, So what I tried hard to do in this class is to sort of come up with an animated example, which will hopefully give you a nice little summary of what's going on in x86 stack, and hopefully will clear everything up for you. Okay, so, and you let me know if I succeed or fail, and I'll be happy to help you clarify anything you don't understand, because that will come into play quite often as we will actually dive into the real analysis. All right, folks. So you can go ahead and you can take a break. Since I went over time again, let's see, 12 minutes. So I can see you back at 8:45. How does that sound? And then we'll do our assembly anime. So if this is going to be assembly anime, like, what do we call it? We're going to be doing a stack chain, right? Is that a right way to call it? Stack chain or stack senpai? Oh, that's even more provocative. Anyway, if you come up, with better names, let me know. You have the entire break to think of that. All right, folks. So I'll see you at 8:45, and go ahead and take a break. All right, folks. So welcome back. And in the last part of this class, we talked about big versus little endian, and we talked about why they're important. And the next thing which I'd like to do is I'd like to talk a little bit more about x86 instruction set and how it works, and and everything behind it. So hopefully by the time when we get to actually analyzing the malware, we will be able to understand everything. Okay, and if you don't understand something, you can always refer back. Okay, so let's take a look at 3 different types of operands which x86 instructions can take. Because as we talked about before, each instruction, it has a mnemonic and then the operands. So there are really 3 kinds of operands that an instruction can take. So one example is an operand can be a register, an operand can be a literal value, or an operand could be a memory location. Let's talk about those. So here is an example of an instruction which says to move the value hexadecimal 42 into the ECX. So in this case, we got 2 operands. One is the destination register, and one is a literal, okay, which is hexadecimal 42. Another example of the kinds of operands that the instructions can take is they can both be registers. So, for example, right here, I have an instruction which takes 2 registers as an operand. So, for example, my destination operand is a register, and my source operand is also a register. So basically, this one says copy the value stored inside the EDX register into the ECX register. All right. Now, also, we can provide a memory address. So basically, when I put brackets around either a register or a literal value, what I'm saying is that I don't want to refer to the actual value in the register, but rather I want to access a location in memory that is pointed to by the address that is stored inside of the EAX register. If I had to draw it, it would probably look something like this. So when I do this, like, let's say that I had 2 instructions, like if I had ECX, and then I had another instruction, completely unrelated, move ECX EAX. Okay, and let's assume that EAX the value of yeah, that's where the animate time comes. The value of let's see, what value do I want it to store? I'll just play it simple, and I'll say the value of 10. Okay. So now, and also I'm going to draw right here. This is my memory, and let's say that this is location 0, location 1, etc., and this is the memory location 10. So memory address 10, like that. Now, here is the thing. So what's going to happen after I execute this instruction right here? Move EAX into ECX. Well, basically, it just means copy the value of the EAX register into the ECX register. So basically, once this instruction is executed, right, ECX is basically going to be equal to the value of 10, because I simply just copied the value of EAX into the ECX, right? So does that make sense? Yeah. Now, yeah. So yeah, great. And now let's take a look at the second instruction. Now, the second instruction says that copy the memory location that is pointed to by the address that is stored in the EAX. So basically, it'll treat the value of 10 that is stored inside EAX as a memory address. And let's say this memory location, it stores the value of, it doesn't really matter, but I'll pick 42 because that's the meaning of life, right? So basically what this says is take the value inside the EAX register and treat that value as a memory address. Now, copy whatever data is stored at that memory address into the ECX register. So basically, it says, okay, so the value of EAX is 10, okay? Because it has brackets around it, I'm going to access memory location 10, and whatever is stored at that memory location, I'm going to copy into the ECX register. So at the end of this instruction, you have ECX is equal to basically 42. Does that make sense? Another way to think about this pictorially is like this. Like basically, when I put brackets around it, I basically mean this. EAX stores a pointer to this memory location. Does that make sense, folks? And Joseph is correct. Yeah, one is value and one is memory address. Make sense? Is some of that stuff slowly coming back to you? All right, great. So, any questions? Are we like clear? All right, great. So now, the next example or the next topic, which I'd like to talk about, is the x86 registers, because it turns out there are different kinds of x86 registers. So first, we have the general purpose registers, and they're used basically as needed by the CPU during executions. Like, for example, if I needed to add two numbers, well, I could probably use the general purpose registers. There are also something called segment registers. Remember, folks, we talked about how your process memory is structured as a bunch of different segments. You have the code segment, you have the data segment, you have the stack segment, and the heap segment. Well, the segment registers, they store the starting address of a particular segment. So, for example, there is a DS register which stores the starting address of the data segment. There is the SS register which stores the starting address of the stack segment, and so on and so forth. There are also the flag registers, and the flag registers are used to keep track of different statuses. So, for example, let's say you perform some kind of a mathematical operation, and if the result of that mathematical operation is 0, then one of the flag registers is going to be set to 1. They can also be used to find out about the results of comparisons. For example, you perform a comparison, and most comparison instructions, they will set the flags according to the comparison result. All right? And finally, there are the instruction pointers. In the x86, there is one instruction pointer register, and it stores the memory address of the next instruction that should be executed. Okay. Sometimes you'll hear to those being referred to as the registers that store the program counter. Okay. Does that make sense? So, any questions about the registers? Yeah. Yep. The good old PC, the program counter. And this is what they actually look like. So in x86, the general purpose registers are EAX, EBX, ECX, CDX, EVP, ESP, and ESI. So you can use them as needed in order to perform your instructions. And those are the segment registers. So CS registers stores the beginning of the instruction segment, or your text segment. SS stores the pointer to the beginning of the stack register of the stack segment. DS stores the beginning of the data segment, and so on and so forth. We'll talk about them as time goes on. There is only one flag register called eFlags. It's a 32-bit register that basically where each bit represents a different status. And finally, we have the EIP register, which is your instruction pointer. So once again, it stores the memory address of the next instruction that you'll be executing. All right. So, and Carl is asking why the E versions and to R versions. I'll talk about that. But basically, in the 32-bit architecture, the x86, the register values start with EBP. In 64-bit architectures, they start with RBP, REX, etc. So since we're in 32-bit, that's basically the idea. So yeah, and I think Joseph raised his hand.
Yeah, so when we were working in 240, most of the time we used the general register, like the full size of the register. But I just wanted to verify, so like AX, AH, and AL would be like breaking up EAX into multiple segments and working with them on a smaller scale, so you have more variables, basically, right?
Yeah, basically. So you're still accessing the same register, but you're sort of accessing like the smaller units of that register. And I will actually talk about that right now. So
okay, perfect. Thanks.
Yeah. So yes. So basically, like I said, usually we will work with entire register values, and that is how you will see the assembly code most of the time. But just be aware of the fact that let's say that I can access my register in different units. So like, for example, by default, if I say EX register, I'm saying that I want to access all of the 32 bits of my EX register. However, if I just want to access the 16 lower bits of the register, right? If I want to access just the lower 16 bits of the register, I can use the word AX. So AX represents just the lower 16 bits of the register. Okay. Now, AX register is broken up into two smaller sub-registers, which allow you to access the higher byte and the lower byte of the AX register. So if I do AH, I'm referring to the two higher bytes of the AX register. I'm sorry. No, I'm let's see. Yes, actually, I'm referring to the one higher byte because each one of those is 4 bits, so 1 byte. So I'm referring to the first 4 bits of the register. So basically, I'm just referencing a single byte. Okay, so I'm just referencing the higher byte of the AX register, and AL references the lower byte of the AX register. Okay, does that make sense? Is that clear, Joseph?
Yeah, thank you.
Yeah, sure. So yeah, and basically, the way in which the x86 architecture evolved, I mean, it started with 16 bits, right? So AX was the highest it can go, and then and then the 32 bits came along, so we got EAX. So, but Intel goes out of its way to retain backward compatibility with older programs. So that's why they did it like that. So older programs designed for x86 will still run without problems because all of the instructions they need are there. And so do all of the register conventions. Yeah. Yep. Go ahead, Joseph.
So we're not going to be actually coding in assembly, are we? We're just going to be observing code that's already been done for the malware and trying to understand that code, right?
Basically, yes. A 99.99999% of the time, that's what's going to happen. Yeah. It'll be more about analyzing the existing assembly, which honestly I think is probably harder than writing your own.
Yeah, I was just thinking that it's actually harder because, like, to put it down, it's pretty straightforward. You just do it whichever way you want. There's so many ways to do something, but to understand it and be able to convert it back to like a higher level would be more complicated because it's only done one way, and you have to understand exactly what that means and take it back.
That's right. And also, you got to remember that the assembly, which you will be dealing with, it will not be the assembly code which was written by another person. It'll typically be the assembly code that has been generated by the compiler. And compilers, they don't really care much about readability because, they're not trying to generate human readable code. They're aiming for things like, performance. So oftentimes, they'll use all kinds of optimizations, which although may make the code, faster and more efficient, it will be much harder to read, if you know what I mean. so yes, you want to be writing code like you did in 240, but I think reading the code is much harder. Hopefully you will think differently. Yeah, seeing is definitely worth it. Yeah, and also, another thing to keep in mind is that some instructions in x86 may actually require you to use specific general purpose registers. Let's think back to our multiply and divide instructions. So, for example, the multiply instruction may look something like this: mul hexadecimal 50, which means to multiply by hexadecimal 50. But what am I actually multiplying by 50? Well, this instruction assumes that the value which you want to multiply by 50 is already stored in the EAX register. Now, and when you multiply the EAX register by the hexadecimal 50, it is possible that your result may exceed 32 bits. So, and basically your result is going to be spanned across the EDX and EAX register. So EDX is going to be storing the higher bytes that spill over from 32-bit register, and EAX is going to be storing the remainder of the lower bytes. All right. Similar thing is true of the div instruction. So if I do div OX75, so I want to divide something by the hexadecimal 75, it assumes that the value which you want to divide has been stored across the EDX and EAX registers. So in other words, EDX stores the higher bytes of the value which you want to divide by OX75, and EAX stores the lower bytes of the value which you want to divide by OX75. So once you perform the division, the actual result will be stored in the EAX register, and if there is any remainder, it'll be stored in the EDX register. So does it make sense? So the point here is that multiply and divide instructions are example of instructions which actually require you to use specific general purpose registers. So you have to use EAX here, and your result will always be stored across EDX and EAX. Okay, similar thing right here. For div, your value must always be stored across EDX and EAX, and your quotient will be in EAX, and your remainder will be in EDX. Okay. When you say a lower bound, you mean?
I think they mean like the first partition of the
Yes, yes, yes. Like basically, so like if I have the value, right? Let me. Oops. Yeah. So let's say that I have a value, right? Some 32-bit value. Let's say it looks something like this. So we have 0, 1. That's 1 byte. So let's see, 1 byte, 2 bytes, 3 bytes, 4 bytes, 5 bytes, right? So now, so this is 32 bits, right? So, and this one doesn't fit. Okay, let's make this one also. So I'm going to do OA and OB. So that's going to be 3 bytes. Need 1 more byte. So I'm just going to do FF, for example, right? So basically, if I was dividing this, then my EDX would be equal to this one, and my EAX would be equal to that one. Awesome, awesome, yeah. Yep, so that's basically the idea on this one. So now, when it comes to the eFlags register, so once again, the eFlags register is 30 bits in size, and each bit represents a flag. So, and as your program executes and as different instructions execute, the flags in this register may be set or reset. And each flag has its own function. So, and here are the different flags. There is the ZF flag, which stands for the 0 flag. And this flag is typically set when you perform some sort of a mathematical operation, and the result of that operation is 0. Okay? So whenever you perform a mathematical instruction, if the result of the operation is 0, then the ZF flag is going to be set to 1. If the result is a non-zero number, then ZF flag is going to be cleared. In other words, it'll be set to 0. All right? There is also the carry flag, and the carry flag will typically be set when you have an overflow. So like, for example, let's say that I perform some mathematical operation and the result is too big for the destination register, for example, then the CF flag is going to be set. Okay, it's basically telling you that you have an overflow. And there is also something called the sign flag, and it's typically set when the result of the operation is negative. Okay, so I perform some operation, and if the result is negative, then the SF flag is going to be set to 1. In addition, it is also set when the most significant bit of the mathematical operation is also 1. Okay, so I do mathematical operation, I get a result, and the most significant bit happens to be 1. So in that case, the SF flag will also be set. Finally, there is the TF flag, which stands for the trap flag, and the trap flag is typically used for debugging. Basically, whenever you set a trap flag, it basically tells the CPU to execute one instruction of the program and then halt. Typically, debuggers make use of the TF flag. So a debugger would basically set the trap flag for a particular instruction. And then once that instruction executes, basically the program will be halted again, and the debugger will basically give the opportunity for the user to look at what happened. Okay, and then when the user says, I want to execute the next instruction, the debugger will again set the trap flag, and the CPU will execute just the next instruction and then halt. Okay, so it's typically used for debugging. Okay, does it make sense? Oh, and Carl is asking, will we translate hexadecimal to assembly code? We will talk a little bit about that, just a little. So All right, so any questions about the flag register?
Professor, what's the purpose of the zero flag? I understand that it's telling you if it's equal to 0, but why is that necessary? Why can't we just see the value inside of whatever register it is?
Yeah, basically, we will learn that there are comparison instructions which set the zero flag if the two values are equivalent. Because
Oh,
basically,
that's right.
the
It's for
way in which
comparison
some of the
purposes.
comparison, yeah, because like the way in which some comparison instructions are implemented, they basically, behind the scenes, they do minus, like they basically subtract one operand from another, and if they're equal, right, then the result will be 0, and if the result is 0, then the CPU is going to set the ZF flag to 1, right? So, and then the branch instruction, which typically follows the comparison instruction, can check the flag. If that makes sense. Mm-hmm.
Yeah,
So,
thank you.
yep, sure. And Aiden, is right as well. Okay. So now there is also the EIP register, which is the instruction register. I mean, again, it stores the address of the next instruction that should be executed. So in other words, it tells the CPU what to do next. Now, attackers really would love to hijack the value in the EIP register, because whatever address is in the EIP register, well, the instruction at that address is going to be executed. So that's why attackers often try to mess with your memory and to inject into the memory from which the instructions are being fetched their own instructions, so that they end up in the EIP register and get executed. Okay, and the reason why that's possible, because we're dealing with a Von-Neumann architecture, right? Because although the program might have been designed to take the data as an input, the attacker has a chance to confuse the system in what is data and what is instructions by by basically injecting instructions into the memory. And because both data and instructions are stored in the same memory, I have a chance to overwrite the existing instructions with other instructions while pretending like I'm writing data. All right? So now, typically, you won't be manipulating EAP register directly. It's sort of automated. Like once you execute the program, the address of the first instruction is loaded into the EAP register. That's done by the CPU automatically. And then as the program executes, automatically the next instruction will be fetched into the EIP register. All right? So any questions about the EIP? I heard some people call it beep. All right? All right, yep. Like that, yeah. Yeah, like a hiccup. So now, what I like to do next is talk about some specific instructions which you'll frequently see in your disassembly. So first, let's take a look at the x86 instruction called MOV, probably the most popular and the most basic instruction. Its job is to basically move data from source to the destination. Now, all mnemonics, all move instructions use the same mnemonic, which is the MOV, right? But the difference is that all of them have different formats. So basically, this MOV instruction moves the value of EBX register into the EAX register. So the destination is always on the left and the source is on the right. That's generally a good way to think about it. Generally, that's how things flow in assembly, that they flow from right to left. So this means take whatever value you have in EX and take whatever value you have in EBX and copy that into EX. Also, we looked at this before, I can also copy literal values into the EX register. So this means take the literal value of OX42 and copy that into the EX register. Now, we can also copy the contents of the memory address into a register. And to do that, we use the brackets operator. Now, what you put inside the brackets operator, it could either be a literal value, which represents a literal memory address, or I could put in a register, or I could even put in a mathematical computation that is used to compute the memory address that I want to access. So basically what this does right here is it will literally copy whatever value is stored in the memory location, hexadecimal 4037C4, and whatever value is stored at that memory location will be copied into the EAX register. Right here, I'm going to copy into the EX register the value that is stored at a memory location pointed to by the value in the EBX register. So in other words, we're just treating the EBX register as storing the memory address from which we want to copy the value into the EX register. And finally, this last example says that I want to first compute a memory address, which is computed by multiplying ESI register by 4 and then adding EBX. This is actually frequently used to implement array traversals. We will see how that works later. And then take whatever value is stored in the memory location, represented by this computation, copy that value into the EX register. All right? So that's generally how the MOV instruction works. Any questions? Oh, and Carla is asking, 4037 is 3 bytes. Let's see, how many bytes we have there? Okay, so we have, so that's 1 byte, 2 bytes. That's a 3-byte instruction. Yep. Yeah. Technically, since we're dealing with x86, all the literal values are actually treated as 32-bit values. So whenever you see a value that is less than 32 bits, you can pretend that there are a bunch of leading zeros in front. So, like for example, this one would be, for example, OX, right, and then 00. 403 37 and then C4. Make sense? Yeah. So just like in this case, I would have 000000 42. Mm-hmm. Yep. Mm-hmm. Yeah. Basically, if you have a value less than 30 bits, you can assume that. Yeah. Mm-hmm. Yeah. That's a good question. Yeah. Mm-hmm. All right. So any other questions? All right. Great. So now, the next thing which I'd like to talk about is sort of like a cousin of the move instruction, but it's actually completely different in some sense. And we'll see this instruction being used all the time. And this instruction is called LEA, or if you want to call it a human name, you can call it Leah. Okay? Or Leia, like Princess Leia. Basically, in some ways, this instruction is similar to the move instruction, but it is used to copy the memory address. So for example, EBX plus 8 represents a memory address, okay? So when I do LEA, EAX, EBX plus 8, what I'm saying is that I don't want to copy into the EAX the value that is stored at the memory location of EBX plus 8, but rather I want to copy the value of EBX plus 8. So basically, I'm going to compute EBX plus 8, and whatever that computes to, I'm going to copy into the EAX. You can think of it as get me the pointer. Okay, I don't want the actual data. Get me the pointer to a memory location. So basically, whatever memory address this is, right, this comes out to, that's what's going to be loaded into the EAX. Once again, not the value that is stored at the memory address of EBX plus 8, but the value of EBX plus 8 itself. So, basically just to sort of really solidify that, like let's say that I got, two similar instructions. Let's say that I have move EAX, the value of EBX plus 8, and then I have another unrelated instruction, LEA, EAX, and then EBX plus 8. So, and let's say that originally, let's say that my EBX is equal to, say, 2. And here is my memory. So it goes from, so let's say this is byte 0, byte 1, byte 2, and this is byte 10. 0, 2, and 10. Okay, and let's say that at memory location 10, I have a value of, once again, OX42, which is the meaning of life. Okay, now, so when I do move into EBX plus 8, well, what's EBX plus 8? Well, EBX is 2, right? And 2 plus 8 is going to be 10. So basically, what I'm saying is into the EX register, I want to copy the value stored at the memory address of 10, which is going to be OX42. So once this instruction is executed, I'm going to get AX to be equal OX42. Now, what about this one? Well, LEA EX EBX plus 8 says that I don't want to copy the value that is stored at memory location 10. I want to copy the memory address of the memory location 10 into the EX register. Well, and basically, it'll just be the same as copying the value of EBX plus 8. So EBX is 2, and 2 plus 8 is 10, so EAX is going to be equal to 10. Do you folks see the difference? Is that clear? Yeah, it's kind of like pointer arithmetic, yeah. And the rest of you folks are clear on this, right? Because when we talk about the stack in that example, I actually have an example of a where a compiler uses that for optimizations. And Joseph's asking, what is the purpose of what? So the purpose of LEA is to load a pointer to a memory location into register. So it's kind of like, get me the pointer of a specific data, if that makes sense. Yeah. Yep. So yeah, so that's basically the idea. Now, so one way to think of LEA AEX EBX plus 8, like we talked about here, is that it's sort of similar, logically speaking, to this. However, to move EBX plus 8. However, folks, this is not a valid move instruction. Okay, I cannot do EBX plus 8 unless I put it in brackets. Okay.
And basically, if you do put it in brackets, you get the value, which is the reason why you need the LEA, right?
Yep, exactly, yeah. Yeah, basically, whenever I put the value inside the brackets, it's kind of like dereferencing a pointer. So like whenever I put EBX plus 8 in brackets, I'm saying that this value represents a pointer. So, and brackets is sort of like my way saying I want to dereference the pointer and grab the data that it's pointing to. Whereas LEA says I want to get the pointer itself. So I don't want to dereference the pointer. I want to get the pointer value itself.
Got it. Makes sense? Yep.
Yeah, sure.
Just clarify.
Yep. And Joseph's asking, it saves you from doing that instruction and a move instruction. Yeah, that's also true. Yeah, that's true. And we'll actually see how a compiler sometimes uses the LEA instruction in some really weird ways, but clever. So now, there are also the arithmetic instructions, such as add, subtract, and increment and decrement. So basically, the way in which those instructions work is, so you have the sub instruction, which first contains what to from the original number from which you want to subtract from, and then the value which you want to subtract. And what the sub instruction is going to do is, so if I have sub EAX 10, it'll subtract the hexadecimal value of 10 from the EAX register and then store the result in the EAX register. Okay, that instruction works in the similar way. It will, in this case, add the two registers and then store the result in the EAX registers. Now, and the operand and the second operand can be either register, it could be a literal value, or it could be an address of a memory location. Okay. Now, and if the result of those operations is 0, then the ZF flag is going to be set, and CF flag is also going to be set if the destination is less than the value subtracted. Okay, so that's basically the idea. And also there are the inc and the dec instructions, which can be used to increment and decrement registers and memory locations. So for example, if I do inc EDX, it will increment the EDX register by 1. And if I do dec ECX, it'll decrement the ECX register by 1. Okay, so that's basically the idea. So any questions?
Can you use subtract and add to, let's say, to do things with the addresses that are in the registers? Say if you want to hop to another location in the memory.
Yeah, definitely. Yeah, all you would have to do is just update the address in the register, and then just use that register inside brackets.
Got it. Thanks.
Yep. Sure. Yeah. So let's now talk about the mathematical add and multiply and divide instructions. So the way in which those work is as follows. So let's say that I would like to multiply or divide a value. So for the multiply instruction, what I'm going to do is I'm going to store the highest bits in the EDX register and then the lower bits in the EAX. So for example, let's say that I want to take a decimal value, that is this, and if I translate that into hexadecimal, and this is where the snake can be quite useful. So I'm going to do hex 5 0 0 0 0 0 0 0 0 0. As you can see, it becomes a hexadecimal value of 12, a 0, 5F, 2 0 0. Okay, so we just need to put a leading 0 at the beginning just to make it all even out. But note, so the first lower 32 bits fit nicely, completely inside the EX register, but the rest of the bits have to be stored in the EDX. Now, the divide instruction is similar to the multiply instruction, except that it divides the 64 bits across the EDX and EX. So in other words, we would load the result into the EDX and EX and then perform the division. So now here is, we looked at those examples before. So like, for example, if I take some value in the EX register and I multiply it by hexadecimal 50, it will store the result across EDX and EX. And if I have div OX75, it'll divide whatever is spent across EDX and EX by the hexadecimal OX75, and it'll store the result in the EAX and the remainder in the EDX. Now, there are also instructions called imul and idiv, which are used for signed multiplication and division. Their syntax is very similar to mul and divide. The only difference is that they assume that the values which you are dividing or multiplying, that they actually have a sign. In other words, it is possible for the value to be negative. Okay? Make sense? So, and Carl has a question. When do they store, whether it's positive or negative? So basically, that's where you would use the I model and I div. Like, for example, if you want to be dealing with the negative values as well. And what you would then have to do is your value would have to be represented as a 2's complement, which is a way to represent sign values. Basically, the highest bit, if it's 1, it means that you're dealing with a negative value. And if the highest bit is 0, it means you're dealing with a positive value. Does that make sense? Now, there are also logical operation instructions which can do bitwise operations. So like there is OR and an XOR, and they work pretty simply. So for example, if I want to XOR the EX register with itself, I can use XOR EX EX. So basically it will XOR the value in AX against the value in AX and then move the result back into the EX register. This operation of this kind actually is very often used for clearing the register because anything XORed with itself will obviously always be 0. Okay? So now let's say that I had a value in the EX register and I wanted to perform a bitwise logical OR operation on EX with hexadecimal 7575. Well, I would do it like this. So basically it would do a bitwise XOR on the EX and then update the value in EAX. Okay, does that make sense? All right. So, and by the way, sometimes you'll see those instructions also being used as no-op instructions. A no-op instruction is basically an instruction that doesn't really add anything to the program's purpose. It is just there for the sake of being there. And sometimes the no-op instructions are used to pad your program so that it nicely aligns in memory, because how the program aligns in memory can affect its performance. So compilers often try to make sure that your program is optimized for optimal alignment. So sometimes compiler may add useless instructions like this just to pad your program to nicely fit inside memory. So that's basically the idea. There are also shift instructions. So the shift instructions are responsible for doing logical shifts and logical rotates. So the way in which they work is I would specify SHR to shift to the right or SHL to shift my value to the left. So basically what happens is whenever I shift to the left or to the right, when whichever bit happens to be the rightmost and I shift to the right, that bit is going to be basically removed from the register and the carry flag is going to be set to store that bit. If I shift, once more, well, basically then the second rightmost bit is going to be taken out of the register and stored in the CF flag. Okay, so basically the bits that are shifted off are lost. Okay, and same thing with SHL. So whenever I do SHL by 2, for example, my register is going to be shifted to the left by 2 bits, and the 2 bits that are shifted off are lost. Okay, now if you don't want to lose bits, if you want, there is also the rotation operations called ROR, which means rotate to the right. So like in this case, instead of shifting, like let's say I'm rotating to the right. So whenever I rotate to the rightmost bit, instead of being shifted off, it would be basically added to the leftmost bit. Okay, that's basically the idea. And same thing with rotate to the left, except that the leftmost bit, which would be shifted off, it would become the most right bit. Okay, and let's see, we got some questions. So Carla is asking, what would a program use shifting for? Oh, shifting is used for so many things. Number one, shifting can actually be used as efficient form of multiplication and division by powers of 2. Because typically a multiply or divide instruction, it actually requires many CPU cycles, whereas a shift instruction requires a single CPU cycle. So performing division and multiplication by powers of 2s can be very efficiently done by shifting. And frequently we want to be able to do operations on bits. I mean, a lot of things require that. So shifting becomes indispensable in that case. A lot of encryption algorithms use shifting, for example. All right, does that make sense? All right. So do we have any other questions?
Have a good night, Professor.
Sure thing. Yep, you too. You too. So, and Carl has a question. When do we do advanced? It shows how malware is written. That's right. That's right. Yeah. Yeah. Yep. We uncover exactly how it's written and everything that it is capable of. Won't tell us everything necessarily, because, like, for example, if malware is obfuscated, we would still need to do dynamic to actually deobfuscate it, because it'll tell us everything that it can do. So every single part of malware's capabilities will be, or I should say, at your brain tips, because you still have to figure out what that assembly does. But it'll be there, that's the point. And Ellie's asking, what's the difference between bitwise and shift? Bitwise and basically means that you're performing some kind of an operation bit by bit. So, like, for example, a bitwise OR would be when you have two binary numbers between each of the matching bits. So, for example, bit 0 of one value is ORed with a bit 0 of the other value, and then the second bit, and then so on and so forth. So and then shift is just a shift. Okay, when we say bitwise shift, we basically mean that we're shifting bit by bit. Okay, so like a bitwise shift of 2 means that we're shifting the value by 2 bits. If that makes sense. Oh, bitwise shift. Yeah. Bitwise shift basically means it's exactly what we did here. We basically shifted, by bits. So, like, for example, here we shifted by 2 bits to the left. So it just means, you're shifting the bits. Mm-hmm. Yeah, because you can have, for example, like a byte-wise shift, where it means, you're shifting by bytes. Mm-hmm. Yeah, and Race is asking, if we do a right shift or a negative number, will it pad it with zeros or ones? So if you do a right shift, it will still pad it with zeros. Now, later on, we'll learn that there is something called sign extend, which allows you to actually control how you pad. So, like, for example, if you're using signed values and you want to, for example, shift to the left, but you want to preserve the sign, it will basically, fill it with ones instead of zeros. But more on that later. Mm-hmm. If that makes sense. Oh yeah, and I think we'll be definitely doing a lot of cool things. I mean, we're just getting started. So in the next class, we will talk about some more instructions, and then we'll talk about the stack. And then we're diving right in. This is just, kind of like a primer. All right, yep. You have a good week, Race, too. Do we have any other questions? Like, ways of programming are weird. Yeah. Yep. They can be weird. All right, folks. So if there are no more questions, thank you again for dropping by. And remember, you can analyze any malware, and peace.